Then
Yes, sir.
okay, I have sent your marks, quiz marks. I
Yes,
think
sir.
you have got it. Okay. So, this week, Friday, I'll be on leave. So Friday, I'll not take your class. Next week, again, that extra class, I'll take it next week. So this week, Friday, I not take your class. Okay. So then,
Yes, sir. Yes, sir.
I have some job in, I have some work in Kolkata. So next week, next week I'll take extra class on Friday as usual. So last times we are discussing the light emitting diodes. Um, Also, we have seen the output characteristics of the light emitting diode and laser diode. In fact, we have seen the requirements of sources that can be used for 5G communication systems, right? And in this context, we have seen this generally semiconductor-based materials are considered for 5G system because we can easily modulate their output beams. Otherwise, if you can choose some other sources, but you need external device. In that case, it will be required external device to modulate the optical beams, optical light. But ultimately, because ultimately within the fibers, it is a simple light. It is actually modulated light that propagates at. So that's why we are focusing on semiconductor-based optical sources. And right now we are discussing the light emitting diodes. And we have seen this, the materials should be of the, direct band gap type materials. But unfortunately, none of the single element semiconductor devices, semiconductor like silicon, germaniums, they are not suitable for light emitting diode or laser diode because they are indirect band gap types. So you need direct band gap type materials where band-to-band transitions are the most probable case. We have seen last times direct band gap type, indirect band gap types. Right? They're the most important things. And accordingly, we have seen this. Generally, 5P systems, it extends from 0.8 microns to 1.6 microns. So the range is divided into two regions. That is short wave regions, longer wave regions. In the short wave regions, generally gallium aluminum arsenide is used, and the longer wave regions, say 1.0 to 1.6 micron regions, indium gallium arsenide phosphide. These are used, right? And also, we have seen last times how the emission wavelength, peak emission wavelength can be determined E equal to, lambda equal to 1.24 upon Eg. E equal to Hg, from that relations you can find out. So they are the relations are most important from numerical point of view. So, and we have seen also discussing also the light emitting diodes. Not all type of light emitting diodes are used for 5P systems. We need the LEDs for which they have high radiance, fast response times, and high internal contact efficiency. Last one is most important. High internal contact efficiency means it related to the fraction of electron hole pairs that recombine relatively. And to get these requirements, two conditions must be satisfied. One is charge scalar confinement, and that is optical field confinement. Optical field confinement. You see, this is one, and these two conditions. And these two conditions can be satisfied if the junction is heterojunctions. I told you what is heterojunctions. If you have a junction made by two different band gap type materials, then it will call heterojunctions. Like say gallium arsenide, gallium aluminum arsenide in the right hand side you can see it. So it's this type of junctions, PN junctions. P-type, N-type, but both can be P-type, both can be N-types because one will be of say, I told you, no, larger band gap, capital suffix means larger band gap, just a smaller band gap. It can be NN also. These things are there. NP, okay, no problems, but NN can also be junctions. This also can be a junction because affinity of electrons will be different in this case. So junctions will be formed, depletion layer will be there, right? Even if you consider the same type of semiconductor materials, N types, both are N types, but of different band gaps. So if you consider these things, then you have different combinations of possibles. I mean, if you consider particularly double heterojunctions. Now, the question is why double heterojunctions? Single heterojunction is why not? Is okay because you see double heterojunction is required because then only these two conditions will be satisfied. And if these two conditions are satisfied, then only you can have high radiance and high efficiency LAD. So these are actually, you see, just like a chain. So you need double heterojunctions, semiconducting materials that can provide the charge carrier confinement and optical field confinement. How charge carrier confinement is possible in double heterojunctions? Because if you maintain the band gap differences, then more carriers can be confined in the. Here actually double heterojunctions. I'll just show you. It can be say NPP structures, okay, NNP structure by these things. So different structures are there. Have a quick look, then it will be more clear. You see it here, NPP structures. You see this is larger band gap, this is smaller band gap. Again, this is larger band gap. This is N-type gallium aluminum arsenide. This is P-type gallium arsenide, and this is capital P gallium aluminum arsenide. Right. So EG1, EG2, and EG3. The band gaps are different. So there are two junctions are there. This is J1, J2. Right. This is the actual is the Fermi level concept. If you just see it, this is the conduction band, valence band for N types. This is for the small P types, a smaller band gap, and this is a larger band gap. Right. So under normal conditions, unbiased conditions, Fermi level will be the same levels. But as soon as you apply you see it for biased, sources are operate under for biased, means N's will be negatives and P's will be positives. Then you see the Fermi level will be shifted. It will be shifted. It will be going downwards. It will be going upwards. Towards conduction band, towards valence band for P types. So accordingly, there will be injection of electrons and holes will be there. So electrons will be injected. Say electrons will be injected in these regions. Similarly, holes will be injected in the regions. So middle layer, this middle layer actually it is called the active layer, right? Actually, instead of junction layers generally here in die structure is used to get more carriers in these regions. So this is the middle active regions where carriers are actually accumulated, and here the carrier recombination takes place. Of course, I told you recombinations may not be always radiative; it can be non-radiative also. Right. So this is the scenario for heterojunction. So you can see there are two junctions. Another question is suppose gallium aluminum arsenide. Gallium aluminum arsenide. How can you make it a P type or N types? It's a 3,5. This is 3,5 compound semiconductors. So if you consider the element from group 2 sites, then you see you can have P types because less number of electrons will be, the holes will be there. And if you consider from the say zinc element like these things, seleniums, if you just consider from the group 6 selenium like these things, then group 6, then it can be, and excess electrons will be there, then it will be N types. So in this way you can have, if you have to replace these elements by the group 6 sites, then it will be N types, and if it is from the group 2 sites, then it will be P types. So in this way you can have it, the N type, P types. Right. Of course, silicon can also be used. So if silicon replaces the group 3 sites, then it will be the N types. If silicon replaces the group 5 sites, then it will be the P type. So silicon valency 4. This is silicon valency 4. So if it replaces 3 sites, excess electrons will be there. And if it is replaced, if it replaces the group 5 sites, then it will be holes will be there. Right. So in this way, you can have it. You can have P type, N types, and etc. Right. So this is the double reactions, and these double reactions is required for the charge carrier confinement and optical field confinement. Charge carrier confinement means if the bandgap differences, say EG1 minus EG2 and EG2 minus EG3 bandgap differences are more, generally EG1 and EG3, they are same. You can see gallium arsenide. They are same. Middle is different, right? So if the bandgap differences are there, say EG1 minus EG2 differences are more, then more carriers can be combined here. More carriers can be accumulated here. Accordingly, more carriers will be combined. So the first condition is satisfied. Second condition, how optical field confinement will be satisfied, because this there are 3 layers will be there. So 3 layers. Middle layer is the active layer. So if just like optical fiber, if you see if this layer refractive index is high compared to this one, then whatever the field optical field is there, that will be trapped within this one. So electric field will be confined within these regions. So that is a so by using the variation of refractive indices among the layers, we can have optical field confinement. By using the bandgap differences, we can have the charge carrier confinement. So accordingly, we can have high radiance and high internal quantum efficiency LED, right? And this LED, you can see it here. It can be 2 types. We'll see it using this concept of operator junctions. There will be 2 types of LEDs will be there. One is surface emitting type LED, and that is edge emitting type LED. And you see in this case, different layers. Apart from these 3 layers, the 2 active layers and the 2 light confinement layers. I mean, confinement layers, either you can say confinement, both carrier confinement and light confinement will be taking place. So these 2 external layers will be the confinement layers. Confinement layers, and middle layer is the active layer. Active layer, right? So these 3 layers must be there. Apart from this, see conventional say contact. You can see it here how the different layers are there. You see this is, and just filling you. Let me check it. The different layers here. This recombination layer. This is N and gallium arsenide. This is the recombination layer, right? Where carriers are recombined. There are the confinement layers outside light confinement layers. This is light confinement layers. Light confinement and carrier confinement layers. Light confinement and carrier confinement layers. And carrier confinement layers. There are also light confinement and carrier confinement layers. Others will be used for metal contacts, other for metal contacts, substrate, heat sink, etc. Those things will be there. So this is the metal contact. They are the 2 end layers at the metal contact. I mean, you have to have positive, negative like these things. So this is the substrate and like these things. Sometimes for lattice mismatch, some layers are also there to reduce the effect of to nullify the lattice mismatch. Right. And if you have any questions regarding these double heterojunctions, you can ask anybody. The concept is most important. Anybody, if you have any questions?
No, sir.
Look, question है कोई? Harshvardhan? No.
No, sir, it is clear, sir.
Okay. So now see the actual structures that are used for fabrication of LEDs. One is, I told you just I mentioned, surface emitting type LED, and that is edge emitting type LED. In surface emitting type LED, you can see it here. This one. This is the substrate. In fact, this substrate. In the substrate, there is a well, and through which a portion of the fiber is inserted, so that maximum number of photons can be collected through this fiber, and coupling will be easy from source into the fibers. So a small portion of the fiber is fixed, inserted through this substrate, and it is fixed by the epoxy materials. Epoxy materials. This is a substrate. And next, the 3 layers are there. You can see it here, these 3 layers. Right. This one is the metal contact. This is the metallizations. Metal contact is a metal contact. This is metal contact. Next, it is a substrate, and these are 3 layers. Say it can be NPP layers or NNP layers. It can be any combinations, right? But double heterojunction. This means double heterojunctions must be there, right? 2 junctions will be there. So, and the middle layer I just mentioned is the active layers, right? On the other side, on the opposite side, other 2 sides will be the light conformant and carrier conformant layers, these 2 layers. And next will be the metal contact. Some isolations will be there, isolation layer, and heat sink is there at the bottom of it. Right. In this case, for surface emitting type, some for construction point of view, you can note it. This is 50 micrometer in diameters. This active area, actually, it is 50 microns. 50 microns. 50 microns in diameter, and it is around 2.5 micron thick. 2.5 micron, 5 micron thick, right? And emission pattern is Lambertian. It is Lambertian. It is called because here actually intensity pattern follows this I0 cos theta. That means it is maximum. Suppose if you consider this one, emission pattern, say like these things. Okay, it is the emission pattern like this thing, right? Emission pattern of LED, just like this one. It is and it is follow here. It is I0. This is I0, and the I0 normal directions, maximum intensity, and at any angles with this theta, that is I0 cos theta. So if this is the characteristics, then it is called the Lambertian. It is generally for all diffusing sources generally are Lambertian sources. There are different patterns, such as elliptical pattern, batwing pattern. Those things are there. But laser, it will be very narrow. We'll see it for laser. This is very narrow. This is wide. But here laser, it is very narrow. That's why divergence is less in case of laser sources, laser diode. Anyway, this is Lambertian source, diffusing source, and the intensity pattern is follows these relations. And here half power beam width, it is 120. What is half power beam width? Means at 60 degree, the power will be half of this I0, right? Half power point, So 50% of the peak power will be obtained at theta equal to 60 degree. Theta equal to 60, then obviously half is there. So I0 by 2 will be there on both sides. So total half power beam width, it is 120 degree. That's what it is mentioned here. You see, half power beam width, it is 120 degree. So these are the characteristics of these surface emitting type LED. So basically 3 layers are there. You see 3 layers. These 2 layers are light conformant layers, carrier conformant layers, and this layer is the active layers, active regions. Okay. So this is the surface emitting type LED. Next, you see another is used, and also one more point here. The light actually here this the active area it is perpendicular to the fiber axis. I mean, fiber axis is perpendicular to this the active area. Generally, this Lambertian pattern means light will be equally bright all directions, from any directions, but of course it will be diminished by this. It will be decreased by these relations I0 cos theta, right? And half power beam these ones. Next, you see the edge emitting type LED. In this case, another structure is here for semiconductor light emitting diode LEDs. This is also LED, LEDs, edge emitting type LED, right? Light emitting diode. Here, stripe structures are there. Stripes are there. You see, this is the stripes, right? Stripe geometry is here. In this case, you see here waveguide effect is here. Right. In this case, the structure in this structure actually will create a waveguide channels, waveguide channel just like optical fiber waveguide channels, so that it will direct the light towards the fiber core, right? And fiber core diameter, since you have seen it is around say 50 to 100 microns, maybe less, right? So in this case, all the stripes are generally the contact stripes are also in this range. I mean 50 to 70 stripes range. It is stripes width. I mean width, stripes width. It is around 50 to 70 microns. It is almost compatible with the fiber core diameters, right? So this is one. Another thing is this active layer, this middle layer. These are three layers. You can see it here also. This is metallizations. Or similar concept is there. Only thing is this here. It is edge emitting. At the edges, at the edge, light will be coming out, right? And you see, this is the metallizations, metallic contact. Next is this is the isolation layers. Isolation layers, SiO2. This is SiO2 layers. SiO2, and next it is your three layers, NPP structures or NNP structures, like these things. NPP structures, the three layers. Light conformant layers, light conformant charge carrier conformant layers, these active layers, next again light conformant charge carrier conformant layers. Next will be substrate, metallization, heat sink. Other things are same as these surface emitting type LEDs. So in this case, this active layer, this it forms an waveguide. So that's why light is more directional in this case. And length is around 100 to 150 micrometers, right? And in this case, emission pattern, it is more directional than that of surface emitters, right? In this case, you see in the plane parallel to the junctions, upper beam width, it is 120 degree, right? Same as surface emitting, but the upper beam width in the plane perpendicular to the junctions, theta perpendicular, you see in this case it is only 25 to 35 degree. So that's why it is the emission pattern is more directional. It is very similar to the laser diode. So laser diode will see the emission pattern is something like this ones, very narrow. So here also it is very narrow beam emission patterns. Emission profile is very narrow, similar to light emitting diode. So these are the two structures widely used for fiber optic communication systems. One is surface emitting type LED, and that is edge emitting type LED. Okay, based on the DA structures. Next, let us consider this internal quantification. Now consider the design aspect or design aspect of LED, right? Here in the beginning, I told you LED must have high radiance, high power output will be there, fast response times will be there, and third one is a high internal quantum efficiency would be there. So And this quantum efficiency is most important because this will correlate every parameters, right? I mean, the power output also will be determined by this eta. Speed also will be affected by eta. We'll see it. So let us focus on this, the how much power you can have it from the LED. How can you estimate the power from an LED, the structure LED, and how it is affected by this eta, internal efficiency. So let us first define what is internal quantum efficiency. I mentioned it is related to the fraction of electron hole pairs that recombine radiatively. Right. So for that, to understand that one, let us consider a p junction device and say p types. If you consider p type materials, then p type things because of further burst multi-carrier injections, electrons and holes. Say suppose a p junction is here, and if it is further burst, whether it is homogeneous junction, heterogeneous, doesn't matter. If it is further burst, then carrier injection will take place, multi-carrier injections, because electrons will be injected in the side, also injected this side. Right. So now if you consider the p type, that means electrons concentration you have to consider. So excess carrier concentrations that you can write in the p type materials, it is delta n, that is n minus np0. What is n? N is under excitations, right? In fact, you can think that only n will be there, but initially when there is no injection of current, still some carriers will be there. That is actually thermally, because of thermally generated carriers, right? Some extra carriers will be there. So electron concentrations because of thermal equilibriums, right? In thermal equilibrium, some concentration will be there. So net excess carrier concentrations will be n minus under excitations minus the and the carriers, thermally generated carriers, right? So n minus np0. Similarly, for n type also you have to consider p holes. So delta p excess hole concentrations, that will be p minus pn0. Here also pn0, it is the whole concentrations in thermal equilibriums. Now, since if you see semiconductor is neutral, so delta n must be equal to delta p. And these excess carriers will be, you see, these excess carriers decay exponentially with times, and this be considered as delta n equal to delta n0 at certain time t, it is e to the power minus t by t. So this will get it at certain time t. This will decay exponentially. How we are getting these relations? Actually, there are two processes are there. So because of this injection of current, there will be excess carriers will be generated, and this excess carrier they will recombine. So whenever it is recombined, then the rate of recombinations will be delta n upon tau. Tau is if tau is a carrier lifetimes, then you see 1 upon tau, that will be the rate of recombinations. So if delta n excess carriers are there, then delta n into 1 upon tau. So delta n upon tau, that is actually the rate of recombinations. So because of recombination, now there will be rate of reduction in the carrier density. So if these two are equals, then you see this dn upon dt, that is the rate of reduction in carrier density, and this is the rate of recombinations in carrier density. So these two are equals and these two are opposite, so we can have a negative signs. And now if you solve these equations with the boundary conditions, with the initial conditions, at t equal to 0, then delta n equal to delta n0, then you can have it. So if you take these ones, you take the log, ultimately you will get the delta n. If you integrate it, you will get it delta n, that is equal to delta n0 e to the power minus t by tau. This will get it. Right. This is the excess carriers. The excess concentrations, right, at time t, right, it decays exponentially. It's quite clear now. Right. Now, coming to this quantum efficiency, internal quantum efficiency in the active regions, actually it is the now because of these excess carriers, the recombinations can be radiative or can be recombinations. So recombinations take place, charges will recombine. So recombinations can be radiative recombinations or can be non-radiative recombinations, right? And the internal quantum efficiency, this internal quantum efficiency, this eta, internal quantum efficiency, eta, that is related to the fraction of electron hole pairs that recombine radiatively. That means it is the ratio of RR by total recombinations. Radiative recombinations plus non-radiative recombinations. So RR is the radiative recombinations rate and RR, and RNR is the non-radiative recombination rate. I told you why. What is this non-radiative recombination? Means energy will be converted to not radiation but some other forms, heat, vibrations, crystal lattice vibration, phonon, etc. So other form of energy you can have it. Right. Anyway, this denominator indicates the total recombinations and the radiative recombinations, right? And if now, since there are two types of recombinations, so the lifetime will be two types: radiative recombination lifetimes and non-radiative recombination lifetimes. So that is tau R, right? Tau R and tau NR. So if we just put it, RR equal to delta N upon tau R and RNR equal to delta N upon tau NR. And if you substitute these things, what will get it? Eta delta N upon tau R by these ones. So I will get it tau upon tau R. This is the most important relations. Right. So the quantum efficiency, internal quantum efficiency, it depends upon this, the bulk recombination lifetimes as well as the radiative recombination lifetimes. What is this tau? If you just delta N, if you just divide it, you'll get 1 upon tau, 1 upon tau R plus 1 upon tau NR, you'll get it. That we are replacing by 1 upon tau. Right. The tau is actually called bulk recombination lifetimes, including radiative recombination lifetimes and non-radiative recombination lifetimes. This tau. So, and we'll see it. Actually, this eta will determine eta will actually if you calculate the power output from an LED, then this eta will play an important roles, and this eta actually should be of high, but eta will be reduced because of some factors like self-absorptions, right? Absorptions or active layer width, etc. All those things. So we'll see it because of several factors. This tau will be reduced. If tau is reduced, then eta will be reduced. So we'll see it. We'll investigate how eta is affected by the effective carrier lifetimes. The carrier lifetimes, including the absorption within the active regions as well as in the layer thickness. Right. Surface recombinations also there. I think I have mentioned here. No, it is not. We'll see it. So, and also when you consider this, the accumulation of charge carriers, actually this LD should be considered diffusion length, that is d tau whole to half. I think it is the basic relations. You have seen it in your basic electronics. So have a quick look. What is this LD? Diffusion length. You see carriers. When you inject the carriers will be excess carrier will be generated in the p side inside, right? And then they will recombine, but they will move before recombinations. They will move a certain distance. That is distance is the diffusion length LD. That is d tau whole to half. How can I have these relations? I think you know it. Have a quick look. Suppose in a semiconductors, the current is due to holes. Then we can write IA equal to current density, A, say A equal to unity area, current per unit area. So if you consider the A equal to 1, then I equal to electrons current will be this gradient of electrons, delta del n x, del n by del x. Similarly, current due to holes will be Q dH del P upon del x. Right. Just a minute. So there the current due to electrons, current due to holes. Next you see, say a semiconductor, say p-type semiconductor. So electrons, if p-type semiconductor electrons are considered, and you consider a thin segment on this p-type materials. So this thin segment, it is of width is delta x, and at x, and so at this point it is the x plus delta x, right? X plus delta x. And if it is a cross-sectional area, it is delta A, then you see volume will be delta x into delta A, right? And now, if you consider the rate of recombinations, now when you are considering the inflow of electrons in the p-type materials, and you're considering this thin segment of volume delta A into delta X, then how many carriers are accumulated in these regions? So that you can calculate it is dN upon dt, rate of accumulations within the thin segment. That will be the here the at this point you have to consider rate, and at this point you have to consider. So difference of these two will be there. So at x it is you see it is dE dN upon dx into x. dN actually it is delta n's into delta A minus dE dN upon dx into delta A into x plus delta x at this point. Difference of these two will give you the rate of accumulations, right? And you see this can be expanded, x plus delta x. So first term will be same terms. Next term will be double derivative d2n upon dx2, etc. This one will be there. However, derivatives, if we just neglect it, then first term cancel, same term will be there. The second term will be dE d2n upon dx2 into delta A into delta x. So this will get it. These ones, rate of accumulation of charge. And also we have seen this, whenever carriers are accumulated, there will be recombinations. So rate of recombination, we know it, delta n upon tau per unit volumes. So it will be, if the volume is delta A into delta x, then that will be multiplied by delta A into delta x. Delta is the cross-sectional area, and delta x is this thin segment. So these two dynamic equilibriums, these two must be sense. So d2, this one, d2 delta n upon dx2, that will be equal to delta n upon tau. This one will get it. So this can be solved with the initial conditions. With these conditions, at x equal to 0, delta n equal to delta n 0, and at x equal to infinity, x equal to, if x is large, x distance is infinity, that times delta n will be 0. So with this you can solve it, and you can have delta n. That delta n will be, you see it here, after solving you will get delta n, and is delta n, that is delta n 0 e to the power minus d tau whole to half, right? And that is, you can write it e to the power minus x by LD. So that LD actually is d tau whole to half. That is the diffusion length, right? Diffusion length. So LD equal d tau whole to half. We'll see it how these factors actually will affect the internal quantum efficiency, right? We'll see it. And if you know these things, their variations, then only you can determine the how much power you can have it from a particular LED. So now let us try to find out the amount of power, how much power LED can emit, right? So for this, you have to consider since it is heterojunctions, and the characteristic of heterojunction is really based on heterojunction. So characteristic of heterojunction is this. Actually, it is so multi-layers are there, and here one factor will be there, that is S, surface recombinations, and another factor is bulk. The recombination I've seen it, but recombinations can be within the volumes and at the surface. So the interface or any junctions, heterojunctions, it is characterized by this ratio S by D by LD, where S is the surface recombinations and D by LD, it is the bulk recombinations or diffusion velocity. Actually, velocity it is called because that unit is in terms of velocity. So, but this term actually represents the surface recombinations, and D by LD, this represents the bulk recombinations within the volumes of the materials. And what is the surface recombinations? You see, if you consider this the perfectly reflecting boundary, then there will be no recombinations, so S will be equal to 0. S will be equal to 0. And for if it is ohmic contact, is here. For ohmic contact, this surface recombination velocity will be infinite. All will be combined, so it will be infinite. So, but this is the two extreme cases, but generally the heterojunction and any junctions, actually it is for any heterojunction, the S is in between surface recombination, it is 10 to the power 2 to 10 to the power 4 centimeter per second in this range, right? In this range, 10 to the power 2 centimeter to 10 to the power, I mean less than 10 to the power 4 centimeter per second. So that is for any typical heterojunctions, right? Now, you see it here. So whenever consider the multi-layer structures and DH structures, then there will be it is also clear now surface recombinations, right? There will be self-absorptions, right? So those things are there. Now with these ideas, now we can calculate the power. But before that, to calculate the power, you have to get the excess carrier concentrations at any point within the active regions. So for examples, this is the 3 layers. Higher band gap layer, lower band gap layer, and again higher band gap layer, NPP structures. NPP structures, right? So you see it here, the 3 layers are there. Now, this is the active, middle layer is the active layers. This is the active regions. I am not showing the other layers, only here 3 layers are shown. This is the active layer. And in this case, your aim is to find these excess carriers, delta N, at any point X. If you can calculate delta N, then you can calculate the power, right? So you consider, actually, you have to get this delta N, you have to solve the charge quantity equations. What is that? That is the d2n upon del nx by dx2 minus delta nx upon tau. Actually, if you see the physical meaning of this, the first term represents the rate of accumulation of charge, just now I've seen it, and the second term represents the rate of recombinations, right? So these two terms. So also this, and if you write this way, then the steady state charge quantity equations will be the difference will be 0. So if you solve these equations with the boundary conditions, then we can find the value of delta nx at any point within the active layers. And if you can calculate delta nx, then we can find out the power emitted by LED. So but this equation can be solved with the boundary conditions. What are the boundary conditions? You see it here. The first one, it is at x equal to 0. At x equal to 0, it is d of delta n upon dx at x equal to 0. And that means the variation of delta n with respect to x, that will be j by qd minus or plus s by d delta n is 0. What is the first terms? It is actually j because of current when it is biased, carriers will be injected. So it is this represents the number of carriers injected. Number of carriers injected. And since S surface recombination is, I told you, carriers will be recombined at the surface. So you cannot avoid the surface recombination. So that is denoted by S. So this represents the number of carriers recombined at the surface. So that is the variation at x equal to 0. So at this interface, you're getting this one. And at x equal to d, if d is the thickness of active layer, then at x equal to d, the same thing will be minus s by d delta n upon d. Here, this term will be 0 because you see it is n consider the electrons only. If you want to, but if it is holes, then of course you have to consider it. Since we are considering one type of charge carriers, electrons, so we can consider this is 0 at this point. Number there will be no an excess carrier number of carriers injected. So this term will be 0. Only surface recombination will be there, s by d delta n into d. Right. And it negative sign will be there because this is the gradient d of dnx upon dx gradient. So this the boundary conditions. Now just 1 minute more. You can see it here. To solve these charge continuity equations, here it is a second order differential equations. You can assume the solutions in these forms: tan x e to the power x by ld plus b e to the power minus x by ld. So if you delta n x it is, then delta n 0 put x equal to 0, and delta n d put x equal to d, you'll get it. So this was. So you'll get two equations, and there will be two variables will be there, a and b. So easily you can solve it. If you just solve it, you'll get the delta nx. This you will get it after getting the value of a and b, right? And once you get the value of n b, you'll get delta nx and delta nx. Then delta nx at any point. So the average charge carriers will be there. That will be 1 upon d, 0 to d. If we integrate these ones, and if you integrate these ones, then you'll get a very big expressions will be there. That is j by qd. Very long expressions will be there. You can see it in the Kaiser, it is given, but that expression is replaced by this tau effective, effective carrier lifetimes, where this tau effective, it is there will be parameters will be there: tau lifetimes, diffusion length, surface recombinations, diffusion constant, and thickness of the active layers. Right. So this will get it average carrier concentrations. From this we can have the calculate the power emitted by ray. Okay, next time we'll see it. Today this much. If you have any questions, you can ask anybody. कोई भी इक्वेशन, कोई भी कॉन्सेप्ट है तो पूछो. आज इतना तक ही है. किसी का कोई क्वेश्चन है तो पूछो.
No, sir.
You can ask. हाँ, किसी का कोई क्वेश्चन है? एक आध क्वेश्चन तो पूछना चाहिए. कैसे समझेंगे? तो तुम लोग सुन रहे हो कि समझ रहे हो? हाँ, कोई क्वेश्चन है क्या? है क्वेश्चन कोई? हाँ, बोलो. नहीं.
No, sir. नहीं है sir.
That slot is there only now. 10 to 10:50. Next week Friday. Next week Friday.
Yes, sir.
Also next week Friday, quizzes will not be there. Notice is that circulated, and quizzes will not be there next week. Okay. So 10 to next week Friday, 10 to 10:50. That extra class I will take.
Yes,
Okay.
sir.
Okay. Okay, then if you don't have any questions, just leave you.